This presentation is entitled Support of Object-Oriented Programming Directly in a Relational Database System. Now, the whole concept of being able to do object-oriented programming in a relational system is unprecedented. It's a big deal. It's revolutionary. And the reason why is because it solves something called the complexity problem. In today's enterprise systems, you typically see potentially tens of thousands of underlying relational tables. In this presentation, we learn of something called a soft schema, which is a clever and sophisticated way of replacing what typically entails the use of thousands of relational tables with a very small, compact number of relational tables.
Support of object-oriented programming directly in a relational database management system. Information technology has a number of challenges associated with it. In today's presentation, we're going to look at two of them. First, we're going to look at rigidity, the inability to easily modify data schemas on the fly. Secondly, we're going to look at complexity. Enterprise systems today oftentimes are comprised of potentially tens of thousands of underlying database tables. To address the IT challenges just mentioned, we're going to look at a technology called TCSQL. In particular, we're going to look at a concept known as soft schema, which provides the ability to support object-oriented programming directly in a relational database, which will consist of the ability to persist the notion of classes and objects, support for single and multiple inheritance, and the notion of polymorphism. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship, and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with N1 and looking at N6. Does there exist a path, directed path from N1 to N6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from N2 to N6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So N2, N6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of N1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal N1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of N1. We see that in green here. And let's find all of the children from all those records. And what we find is we get N2, N3, N4, and 5, N6. So in fact, that represents all of the descendants of N1 here. Now, one of the unique things about transitive closure with respect to TCSQL features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. One of the features of TCSQL is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1. which has properties A, B, and C, and a hazard relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is-a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. In the last slide, I introduced the notion of a soft schema. So let's look at the difference between this thing called a soft schema and a normal, what I would call a hard schema. So here's a conventional relational table, a customer table with 3 columns, full name, phone, and product. I claim this can be represented as a class graph as follows. So we have the name in the table here called customer and the 3 columns indicated here. Relational tables associated with a soft schema equivalent look like the following here. So we have a class table here. Notice this first record here is has-a of type connection. So even the connection type here is shown here as a row in the class table. Now we have the name of the table here, customer, and the 3 column names here, which show up here as records as well. We also have the class connection table. I should point out here that in this slide here, we're showing the class table as having an ID field, which uniquely identifies the row here. This actually more accurately represents the true implementation here. So our class connection table is really ID values here. So we have a parent and child ID columns, and the connection type here we see a value 3, which is a has-a. Now that represents the schema for the table here. Let's look at the equivalent object graph here representing the actual data in the table here. So we have a row here. So we have a customer record here which has 3 fields, full name, phone, and product. And now we see the values filled in for these particular graph nodes here. So let's look at the soft schema tables associated with the object graph here. So we have an object table here, and now we have the name value pairs that you see reflecting this graph here. And we have an object connection table here representing these connections here. So what I've shown here is that the information that you would normally see in a hard schema here, its equivalent in a soft schema is reflected here. Now what happens if we were to add another conventional hard schema table here? So we have a supplier table here with columns company and vehicle here. What changes over here now? Well, first of all, we add new rows here in the class table representing the supplier table and columns company and vehicle, and we would also have equivalent appropriate rows populated in our class connection table. Representing the actual data of this supplier table here, we have records added in the object table here. There's our name value pairs, and appropriate records added to the object connection table. I did not bother showing the transitive closure tables here. The thing to point out here is that every time we add a new table, what you would normally see in a hard schema, there are no tables added in our soft schema here. The only thing that are added are new rows to these existing tables that you see here. And so it is by this approach we're able to take a conventional approach of a hard schema that may entail possibly tens of thousands of tables and do the equivalent with this notion of a soft schema representing what you see here, 4 tables plus the 2 additional transitive closure tables. With this soft schema model, let's look at an example of instantiating a class instance here. So we have a class graph here, and all the data in this graph can be represented with 2 tables here. So we have a class table representing all of the nodes of this graph. We have a class connection table showing all of the connections here. Now I didn't bother showing all of them. I just showed a few of the rows here. Okay, now let's look at what happens when we want to instantiate this particular node here, a boy. What we're going to do is instantiate this boy. We're going to call this instantiation Andy here. And what is going to happen behind the scenes is TCSQL is going to figure out all of the particular properties that need to be inherited here, and it will populate appropriate object and object connection tables here. And these 2 tables will represent an object graph that looks like the following here. Notice here that I've introduced a new kind of relationship, a has-not relationship. TCSQL supports the ability to do inheritance override here. Now, if you were to implement this in an object-oriented language such as C# or Java, this is the object graph equivalent what you would get here. Now, the real power and beauty here is I did this directly in a relational database using standard SQL. Now, just so you realize, the capability I just demonstrated to you I consider pretty powerful and sophisticated. So, in reflection of that, I've been corresponding with some fairly big hitters here. You might recognize most of these names here. And so my goal here is to try and evangelize this rather revolutionary technology. So why is this valuable? Well, first of all, I would point out that the object-oriented magic is directly in the database, not in any application. In a typical N-tier architecture, you typically have the intelligence in the middle layers here, and what I've demonstrated is that in this case, with a soft schema, much of the intelligence is at the back end here. But one real important thing to point out is that this offers the ability to do unbelievably powerful queries directly on objects here. That will be demonstrated in future presentations. Another value here is it solves what I would describe as the rigidity problem. I demonstrated the ability to add the equivalent of new hard schema tables simply by adding new rows in the existing 6 tables here. It also solves what I call the complexity problem. A normal conventional enterprise system potentially may contain tens of thousands of underlying database tables, and we're replacing them here with a mere 6 soft schema tables here. I claim that what I've demonstrated to you is actually revolutionary. In fact, this technology has been used by a number of companies, and it has demonstrated a tenfold reduction in application development and maintenance. Now, I should point out something that oftentimes when you hear something is revolutionary, a lot of times a red flag goes up, because typically when something is revolutionary, it usually implies you have to throw away your legacy technology here. The neat thing about the soft schema approach is that it is evolutionary at the same time it is revolutionary. So those 6 soft schema tables merely sit next to your existing enterprise system.